Cathedral. What class is it for? Oh, okay.
Okay, so for this first thing here, I don't want any talking. I want it completely on your own to get your brain going. I know it's been a bit, but this should be a gradual way to get us back into thinking about chemistry. There's 3 boxes right there, okay, on your own, so don't talk to anybody else, don't look at their paper. I would like you to draw me a particulate diagram of a substance as a solid, a liquid, and a gas. Particulate means at the molecular level. So we're going to say you can just draw them as circles, so just make them like bouncy balls. Okay, if this substance, let's not pick water, because water's a little different in some ways, but just say any other substance. If it was a bouncy ball, what are the bouncy balls going to look like as a solid? What are they going to look like as a liquid? And what are they going to look like as a gas? I'll give you about 3 minutes to draw a picture in each box, okay? Ready, set, go. Looks great. Looks great. Don't talk to others. Should be quiet. So like the same substance, but what would it look like as a solid? What would it look like as a liquid? And what would it look like as a gas? Set your pencil down when you're done. That way I know you're done thinking. So we have 2 days scheduled to be running.
Do you want to try to like the glass around?
Oh, the sticker's right in the way, huh? I didn't even notice that.
Can't see.
I like make it so you can see it, but you can't see it. Okay, in walking around, it looks like we're on the right track, which is a good starting point for this unit, okay? Once again, Chromebooks, cell phones, other things should be put away. Don't veto your right to a retake the first day you're starting the unit, okay? So, in this unit, some of this stuff should be like things you've talked about since elementary school. But then, hopefully we'll be looking at maybe from a different way as we look at solids, liquids, and gases, okay? So you should have something along the lines of the solid molecules are very packed close together. Liquid molecules more spread out. If we could make it as like a simulation, we'd actually see movement within it. And then gases, much, much more spread out. So if you have that, those 3 ideas, you can have a smiley face for that. Out of curiosity, does anybody know why I said to not do water? Why is water a little problematic, Blake?
Well, it's got like, so.
All right, let's listen to Blake, everybody.
It's.
Okay, go ahead.
replied. I can't remember
Oh,
why.
yeah, you lost your brain.
Why?
It's okay. I know spring break. My brain is still trying to figure out how to speak. Anyone know why water would be problematic, Sam?
Because it has hydrogen bonds, it'll stick together more than the average liquid.
Good. And as a solid, what's unique about water as a solid?
It gets bigger.
It actually gets bigger, right? It's less dense than it is as a liquid. Because of those hydrogen bonding, it actually creates those cool like snowflake-like structures and spreads the molecules out. So actually the solid, there's more space between them than there is in the liquid. But water's unique in that sense. Pretty much every other substance on Earth, the solid's going to be closer together than the liquid would be. Okay? So as we look at this, a few things as you kind of look at the trends, right? That as we go, okay, so, whoops. Okay, you don't have to write these in there if you understand what it means. There's just talking about what it does. But in those arrows there, so going from this way to this way, what's changing?
How fast they're moving. How many?
Good, moving faster would be a good thing, right? Faster in movement. And then reverse-wise, going this way, how else could you describe? Slower, or you could say like
There's
more
more
compact,
bonds.
right? Closer together, more intermolecular forces going on, are kind of what you can show on those two lines. Okay? All right, now we mentioned this before, but it's been a bit, so let's bring you back up. Okay? So why does water exist as a liquid at room temperature, while carbon dioxide exists as a gas at room temperature? So how can two things at the same exact temperature, one is a gas and one is a liquid, what's the difference there?
It has different boiling points.
Good, so there's one, it has different boiling points, but let's go deeper than that. Why? Why do things have different boiling points? Easton?
One's bonds aren't as strong as others.
Yes, because of intermolecular forces, the unit we just came off with, right? If something has strong intermolecular forces, the molecules hold together. And so it makes it harder for them to come apart, aka a higher boiling point. If something has like no forces whatsoever, then naturally things will spread out, right? If there's nothing pulling the molecules together, then they're just going to stay apart from each other. So that's the difference is carbon dioxide, which, right, is in our air that we breathe it out, okay? It has only London forces, so it is very not attracted to hold together. While water, we know, has all three forces and holds very strongly to one another, okay? Now, in this unit, two key things, if you look at our ICANN here, so our goal by the end of today's lesson is that you can analyze data in a phase diagram to determine how temperature and pressure affect the material's freezing point and boiling point. Okay? Graphs is going to be a really big theme in this unit, looking at different types of graphs with pressure and temperature. So on that note, we need to understand these two things. So let's first talk a little bit more about temperature. Okay? So in chemistry, we need to make sure you're understanding the word temperature correctly. Because as I would say a normal human, most of the time when we hear temperature, we think hot and cold. But that's not really what temperature is about. Temperature is the average kinetic energy, aka the movement of the atoms of a substance. Thank you much. Okay, so when we're talking about temperature changes, we're talking about making the molecules move faster or slower. But it doesn't always mean hot or cold. Okay, hot is a very relative term, right? I think I mentioned this before, like what is hot to one person doesn't always even feel hot to the other person. And cold as a measurement doesn't actually even exist. Right? There's no like value for cold in science. There's only values for absence of the heat, okay? So keep that in mind as we look at temperature. So if we were to do a very boring experiment, okay, where I had a jar of ice, we put a thermometer in it, and then we just started to heat it up. Okay, we heat it up, we let the ice turn to water, and then we let the water turn to steam. It's very boring, but it's kind of cool on what data you would actually get out of it. You would always develop, no matter what the substance is, you would always get a graph that looks something like this. Now, where they fall on the numerical scale would vary, whether what substance it is, but they would all have this kind of climb, flat, climb, flat, climb pattern to that. This is what we call a heating curve. So think of, because you're heating the substance through the various phases. Okay, so let's go ahead and label what each part of this diagram shows. Okay, starting down here, this whole slanted line represents while our substance is still a solid. I'm gonna have little things on here. Can you read that black okay?
Yeah.
Yeah. So in terms of water, if I hope you have a tangible thing, right, this represents while it's ice. By the way, this right here is temperature, so as the temperature is going up, right? Now, the point at which it goes flat is now the point it starts to change from a solid to a liquid. But it's not actually either while it's on this line, it's both. So this is what we call the melting / freezing line, depending on which direction on the line you're traveling. Right? Melting would be going this way, freezing would be going that way. What's interesting though is while that process is happening, while the ice is actually melting, the temperature, if this was water, would be at 0 degrees Celsius the entire time. The temperature doesn't change while it's changing phase, even though it's still on my hot plate. So any thoughts of why that is? Why does the temperature not go up even though I'm putting heat into it?
Because it's taking away all the heat when it's melting, it's using that heat to force it to melt.
Awesome, you can have some ideas of that. So all the heat is being used to break the intermolecular forces, not make them go faster. Because keep in mind, temperature is just movement. And if temperature is going to go up, that means they have to start moving faster. Well, they can't start moving faster until you start breaking, right? The little molecules, think of our little water things with the magnets. You've got to break the magnets apart before they can actually start moving faster. But then, once they all break apart, now they can start moving faster as a liquid. All right, so this whole line represents while it's in the liquid phase. So for water, water melts at 0, and what does it boil at in Celsius? 100.
So much easier.
That's why the Celsius scale is so much easier. It's much clearer. Right, so between 0 degrees and 100 degrees, it's all liquid water. Right, it's all liquid. Obviously, it's warmer liquid and colder liquid, but it's all water. Porter.
When there's the up and down thing with solids, liquids, and I'm assuming gases, it is where the temperature is actually changing, but the state isn't. And while the plateauing is where the temperature isn't changing, but is instead changing the internal stuff.
Very good. Yep, now it's kind of breaking those bonds more apart. Yep. And on that note, we see the same thing here next on our next line. Oops. Which is, no, let it go away. I'll bring it back here in a second. Okay, the boiling and condensing. Once again, boiling going hotter, condensing is the opposite of boiling and getting colder. But while that phase change is happening, the temperature doesn't go up. But then once you're able to eventually get it all to a gas, and obviously this would have to be a closed system thing where I don't let the gas just float away because I want to heat it up, then you could make the gas or the steam get hotter and hotter and hotter. But it's actually impossible to get the water to be above 100 degrees, at least under normal pressure conditions. And that's when we'll start talking about our second factor of how pressure plays a role into this, okay? All right, let's go back here, and then we got some blanks to fill in. If you flip it over, and we have the graph labeled. Okay, so fusion, by the way, is just another fancy word, and we've used it before, which sometimes I don't love that it has two definitions, but fusion is also used to describe melting. when we're talking about the phase change. So this right here is sometimes known as the change of fusion as well. Okay? The kinetic energy, once again, does not increase during the phase change because all of it is being used to break those IMFs. So this is kind of what Easton was telling us about, that the phase change energy is being used to break those intermolecular forces. Okay, and then melting point is the point at which a material changes from a solid to a liquid. Once again, the kinetic energy of it is equal to, or it's all about the force between them. So they don't actually go faster yet because it's being used to break them apart during that melting process. Okay, now boiling. So boiling is the temperature at which a material changes from a liquid to a gas. Okay? The kinetic energy of the individual atoms causes the vapor pressure to equal the atmospheric pressure. And we'll talk more about this with our demonstration here in a second. The vapor pressure is the pressure exerted by the gas molecules. So once you get that written in, then we'll look here at our beaker of water. Say that again. Oh, we'll get to that in a second. Sorry. Okay, everyone eyes up here on my beaker. Okay? So I have a beaker, it's just plain water. Okay, fill it up at the tap. Okay? So imagine with me if we could magic school this in here, and we're just gonna imagine them like bouncy balls again, because sometimes that just simplifies versus bigger structures. Okay? So imagine all the little bouncy balls of water in there, right? They're in there. Are they moving? Yeah, because that's what makes it a liquid, right? It's because they're moving, so they're kind of sliding past each other. Kind of like maybe like mosh pit type style is how I imagine liquids, right? Because they're close together, but there's movement still. Maybe not a super packed mosh pit, like a little space, right? Okay. In order for these to become a gas, two things have to happen. Well, kind of one, but in two parts. These have to overcome the pressure that is pushing down on them. So we live in an ocean of air. We talked about this before. Did I draw a mountain on the board? Have I done that yet? Sometimes I forget between AP and Gen Chem. Okay, so a way to think about our Earth is an ocean of air. Okay, so that's a mountain. Okay, there's the snow cap. Okay, so in terms of the land area, if you are at the bottom of the ocean, is there more or less air at the bottom?
Wait, we talking bottom sea level or bottom of the sea?
So down here on the Earth is sea level.
Oh, yes. Okay, sea level?
More.
Yeah.
And there's more air, which same thing at the bottom of the actual ocean, there's a lot more water, right? Because of all the water pushing down on it. And then as you climb up, what happens to the air?
You get less.
It gets less and less and less, right? So we are in an ocean of air surrounded by us, but depending on what level of the ocean you're in, there will be more or less, right? Like if you don't, you can in a sense feel it if you take your hands. I'm gonna go like this. Take your hands, bring them out, and then wave them back and forth, right? You can feel the ocean around you. Can you feel it? Right? Now, it's not like real water where it's not dense enough for me to grab it with my hand. Otherwise, we could fly, right? There's enough air. That's how you would fly, is because then you could push the air down and you would go up.
You could hide a ton of air and then release air and you're going to push it down and you're going to fly.
Yeah, you could somehow go in like a compressed air tank.
Yeah.
You'd also need an air mask because it'd be too much oxygen for you to breathe.
But like theoretically.
But it'd be
you
like
could fly.
scuba diving, how you have to wear a mask, but you could fly. Or you'd be swimming, right? Is flying actually flying, or is flying just
$1 billion
swimming?
idea right there. $1 billion.
I'd pay for that.
So with this idea, as we look at changing from a liquid to a gas, that's really the big thing, is it has to overcome the air that's pushing down on it. Once these get enough movement to come out, then they can turn to a gas. So what we're going to do here is we're going to remove all of the outside pressure pushing down on the liquid. So we're going to create a vacuum chamber.
AKA space.
We are experimenting on water.
Okay? So this right here just seals it in. There's a tube right here hooked up to my pump. This is going to just suck out all of the air around it, meaning there's no air pushing down anymore. Does that make sense?
It's gravity though. Gravity will keep it.
Yeah.
Sure, it's sealed up here.
Listen, I know, but we're not tapping gravity on the water.
Okay, ready?
Gravity has to.
You just shatter the glass.
So we're just hearing all the air is getting pulled out of the system.
Well, yeah, there is. Water is
It's obviously not an instant process to pull out all the air. It's very exciting. Oh. So what are we seeing it doing?
It's pulling the air.
So it's boiling because all the pressure above it has been removed. Right? And so now the water has nothing holding it down,
Does,
and so it just starts to turn
does
to a
like
gas.
boiling water on the stove mean that you're like, I don't know, that it like pushes against the,
Sorry, I cannot hear anything. Say that again.
like the pressure that's coming in naturally and stuff? Does when you're boiling water that the boiling just push against it or something? I'm not making sense.
Okay, so let me build off of that as we talk about this. So as I pull it out of here, normally, if you were to have a pot of boiling water on the stove, you take it off. It's maybe been like 30 seconds. How would the water feel?
Pretty warm.
How's our water feel, Cam?
Except boiled.
Right? So it wasn't about that it needed, in this case, because all pressure was removed. Right, we'll get a second witness in case I paid Cam off. Right? Third witness since they both run for me. I'm not tricking you. It's cold, right?
That's actually.
Okay, but because all the pressure was removed, the molecules just
It's cold.
spread out, right? So to give you another demonstration here, let's do it with a gas now. Okay, so balloon, filling it with gas. Okay. So what are the little bouncy balls in here doing?
They're there.
Yep. That's what is causing it to hold its shape, right? But if we remove the air we can't see around it, let's see what happens.
Zero G.
Oh. That sticker's kind of annoying. Okay, is that better?
Yeah.
Okay, let's seal it back up here. Okay, ready?
Wait, what the? What?
Pop.
What the heck?
So what happened?
Yo, it looks like the thing from
It
Mario, you know,
expanded
like the
because there
weird.
wasn't air around it pushing it.
Yeah, so the gas molecules,
Wait, so would it just fill that entire space?
theoretically, I don't really want it to pop,
Do
but
it more. More.
You get stuck.
it kind of looks like it's getting stuck, like.
Yeah, so you're gonna have to like turn.
Well, and it might be somewhat limited to how much gas was inside of it, right? So inside of it was gas, but in the normal air, gas is also pushing on the outside of the balloon. But if you take away the outside pressure, then the inside ones
Oh wait. Look.
Well,
Oh.
it's good. Is
can
it
just push out more, right? Because there's nothing holding them
Pressure's
inward.
Well, I think isn't there still oxygen in there because it keeps blocking the-
wait, don't do anything. It's
Yeah,
floating.
would it just go straight? It's
Yeah, I'll
stuck on the wall.
So it's going to the same side, but well, not really.
No, it's stretched.
So it just goes back to the
was
same
pretty
side
much
as it was
the
before.
same size.
Yeah.
the heck?
Go ahead, Blake.
Okay, so back to the water.
Yeah.
Right, the water was cold.
How
Huh?
How was it cold?
That's so in space. If you throw water out, it's gonna freeze because there's no space is a void. There's no like heat. So if
pressure.
you were to put hot water in that and leave it for long enough, will it will it cool down faster than if you just like left it on the table?
Let's see, you're saying if I put hot water in a vacuum chamber,
Yes.
would the vacuum chamber make it cool down
Right. 'Cause-
faster?
Yes.
Well, if anything, if it was already hot, it's gonna just start evaporating. Then it would start boiling really quick. So like if I heat up my beaker beforehand, because it took like what, maybe 30 seconds for it to start bubbling.
Yeah.
So if I started with warm water, as soon as I kicked it on, it probably would start boiling because they're already close to like coming out. And so then when you remove the pressure, then they can probably just start coming out even faster. We can try it in a little bit if you want. I can throw the beaker in the microwave.
Yes.
Yeah.
What do you think?
So, this is kind of a weird question, but like, have we ever done this in human?
That
Put a human in a vacuum chamber.
Yeah, like, and if we did, would his body go like bigger? It's called just go bigger.
well no.
Yeah, that's why you have to
Without
wear a
the suit,
pressurized
without
suit
the
in
suit.
space. Because if you weren't, all your insides would want to come outside.
It's like
Oh my god.
So wait, so
Pretty much.
it
Because
was
all the
like-
air like in your lungs, right? And then like all your blood would start to boil.
oh.
So you wouldn't like freeze over, just become a cold corpse in space. You would just get
Wait,
you
so
would just explode and have your guts to the stars.
so every movie that is like Guardians of the Galaxy.
Yeah,
Those are not accurate.
It's
That's
wrong.
fake?
It's wrong.
That's wrong.
Aliens.
Well, have you seen Gravity?
No.
No, because they're
Gravity.
Yeah.
Because they need to keep that PG 13 rating.
It's already that temperature when I started. Because boiling just means to go from a gas to a liquid to a gas. And if I can take away the pressure pushing down on the liquid, so think of me, I'm holding the bouncy balls and that's how it's right. But in the vacuum chamber,
I
it
get
goes
up
away.
with
So now the bouncy balls start.
Bro, because it's through the track, it's PG 13, bro.
Like hot.
rated R very quickly.
Like boiling has to be hot. So, cheers.
So wait, what do astronauts do to their suits that make them alive?
So they have pressurized suits
So it's
that like help combat the pressure, the lack of pressure. It's similar to an airplane, right? Like how airplanes are pressurized.
on Earth, would you like die?
Say that
Would you
again.
be pressured to death if you were on Earth?
No, because they're pressured to be like normal feeling. Once again, it's the same exact thing like in an airplane or even in a sub. Because pressure changes as you go up in the air or as you go down in the ocean. And so they do the same thing on an airplane of where they pressurize the cabin. Have you ever talked about like that, right? They pressurize the cabin when you fly for the same reason.
That makes sense.
Yeah, great question though. Sam. Say that again. Not that I know. Well, I mean, I guess in a sense that's what an airplane was kind of like, right? So we're pressurizing the airplane. Oh, I bet. Yeah, you could for sure. And then you would be like, I can't stand up because the pressure's too high.
Yo, you could underdo an airplane's pressurization. You could like do the opposite of pressurization.
Bro, like, I think I see the first day footage.
Oh yeah.
Question.
Yes.
How do you pressurize a helicopter?
You can't.
Because like,
You can.
can it not go high enough?
That's a good question. I don't know about enough about helicopters to say, but that'd be my guess is that they don't. But they don't go as high as airplanes.
Yeah, airplanes are what, 20?
And so I'm guessing probably similar to like, I don't think like small airplanes, I don't think they like do it, but it's because they don't go as high in elevation. That's a good thought though, I never thought about helicopters. Okay, come up here everybody, so this is your next blank to fill in. Okay, so when we talk about standard conditions, okay, focus back up front here. So standard conditions is considered 1 ATM. That's probably the most familiar unit of pressure, maybe you're familiar with. Some other units of pressure, just in case you see them on a graph, we have what are called kilopascals. Okay, kilopascal is a measurement of pressure, or millimeters of mercury is also a measurement of pressure.
Wait, what does HD mean?
Mercury, millimeters of mercury. Because they've used mercury before as a gauge of pressure, similar how they used it in thermometers. It used to be used in barometers, which measure pressure. But this is considered sea level. So when you go to sea level, you're at 1 ATM. As you go up, so we're not at sea level, are we above or below 1 ATM?
Below.
Above. We have less pressure, right, than sea level. So, right, there's more pressure at the bottom of the ocean than as you go up. Okay? All right, let's look at our first type of graph here. We're going to see 3 different ones. We saw our heating curve one. Here's another one. So keep in mind that boiling point is the point at which vapor pressure equals the atmospheric pressure. So once those 2 things are equal, it will boil. Okay? Which is why when I removed all pressure, our beaker could just boil right now. Okay? So in this question it says, what is the boiling point or boiling temperature of chloroform?
60 degrees Celsius.
Okay? So here's our chloroform line. Okay? This is vapor pressure, this is temperature. Okay? What am I looking for with pressure? Notice our unit here, we're in a kilopascal. So if it's going to boil, what does the pressure need to be at?
101.3.
The same as the standard. So 101.3 is all the way up there, which means chloroform will boil at 60 at standard conditions. So it's all about just matching it to the standard conditions. Now obviously this is taking into account that we're boiling it at sea level. Obviously we'd have to look at it differently. Okay? Alright, for a smiley face, see if you can find this answer. Don't say it out loud, just write it on the blank. For a smiley face, fill that one in. What I really wanted, I forgot. Maybe I'll try to do it next time. It's really fun. It's similar to the balloon. You can put a peep in a vacuum chamber. And then the peep, like the balloon, has a lot of air trapped inside of the marshmallow. And the peep gets bigger and
See,
bigger.
what happens if
And
you
since it
put
was
this-
just Easter, I was like, oh, I should bring a peep.
What happens if you put this in?
Being that the container is rigid, it wouldn't be able to expand. Okay, if you said close to 80, have a smiley face. It's not like quite on 80, but you're reading from a graph.
So,
Maybe like
choose my
78.
I put 79.
Perfect, yeah. I'd say anywhere from 75 to 80. Give yourself a smiley face.
What?
Okay, questions on these types of graphs before we look at another one? Okay, before we go to the next one, everybody stand up really quick. Let's take a quick stretch break. Stand up and stretch your legs. All right, have a seat. All right, back up right here, everybody. So as we continue our discussion, keep in mind, higher altitude means thinner air, meaning less pressure. Right? As you go up in the ocean, there's less pressure, just like in the regular ocean, right? So in our ocean of air, same concept. Okay? So if I'm looking at this graph in terms of where we're at in Lehigh, how would I look at it differently? How would it change if I'm trying to find the boiling temperature of water in Lehigh?
Would we have to look at the sea level of Lehigh?
No, wait,
It's
what?
not
I know you meant you just said it weird.
I know, like,
KPA.
You said, I know what you're saying, Gavin. What do we need to know for Lehigh?
The pressure.
altitude.
There you go. Yeah, we just need to know what is the altitude of Lehigh to then look at it differently. So, altitude or the pressure
Is about 84.
2 kPa
in kilopascals,
is 84.2.
Which is roughly 95 degrees.
so
So that around 95 degrees, water will.
so 100 is kind of off, but
It's
it
close
says
to
today we're at like 104 kilopascals.
Wait. 104?
So here's 100,
Yeah.
here's 101. So we gotta go up a little bit more.
Your but
and
That
then
number's wrong.
that number's wrong.
84.2.
Wait, what number? Oh,
Can
sorry.
you not see it?
No, this is the one, we'll use this one. I didn't see that there was one, so we'll use that one today. Pressure varies with weather, right?
Yeah.
But this is what I look at. Okay, so go to 84.2 on the graph. Match it up. So,
95, 96.
95-ish. Okay, don't say it out loud. Don't say it out loud, but I want you to ponder this question, okay? Everyone close your mouths. Okay, now as we keep moving on with this discussion, I want you to ponder this question. So water boils at the top of Mount Everest at 68 degrees Celsius. What would this mean about the time it would take to cook mac and cheese? Would it cook faster, slower, or the same on top of Mount Everest? Don't say anything out loud. So if I were on top of Mount Everest and I have a hot plate and a pot, and I'm going to make me some mac and cheese on the top of Mount Everest, the water will start to boil at 68 degrees. Is that going to cook my mac and cheese faster, slower, or the same, and why? Okay, don't say anything out loud. Just ponder that for a second. Versus like somebody doing it like here in Lehigh where it's not going to boil until it gets to 96 degrees or whatever. Okay, turn to your table buddy and share with them your thoughts, and then we'll have you share Chem. Ready, go.
It'd be faster to take quickly, but I know there's none of this coming on, so.
I think it's gonna be the same.
Because it has some air in it. It once again doesn't have much room to expand, like the outside's pretty, unlike latex, which can like push out. I'm guessing your baby puff up a little.
It's not, it also doesn't hold.
Yes, like the air isn't like trapped inside. It's like the marshmallow doesn't like grow as much as the balloon does because it only has so much air inside of it. Okay, Cam, let's hear your thoughts.
So I think it would be faster because the boiling point is lower, so you get your boiling
boiling point faster?
Who agrees with Cam's conclusion that it's going to go faster? Who said something along the lines that it's going to go faster?
Gotcha.
I heard some of you say faster. Now you're all being shy about it.
Well, my mind got
Oh, but now you changed your mind all of a sudden.
well, not all the same.
Oh.
Oh, that's
Oh, okay. Easton, let's hear your thoughts.
I think it'll actually cook slower because the temperature, just because it boils sooner, it still takes the same temperature to cook the mac and cheese. The mac and cheese hasn't changed at all, so it'll cook slower.
Very good. So it's that thing of where you need to separate in your brains, everybody, that boiling means it's hot enough. The water's not going to be very hot if it's boiling at 60 degrees, and what's cooking the noodles?
The heat.
The heat. It's very similar. On Thursday, we'll bring in some liquid nitrogen. I know it's been delayed, I've said that a few times, but we are going to bring some in. Right, with the liquid nitrogen boils at negative degrees. If you put mac and cheese in liquid nitrogen, it's not going to cook it, it's going to
Freeze it.
freeze it because it's cold, right? So boiling doesn't mean,
So it would be slower? It would actually be slower.
so on top of Mount Everest, it would take a lot longer because your water's not very hot. Versus like here, your water would get up to 90 something. I don't even know if it would cook. I don't know if noodles can cook at that temperature. Right, or if they just like slowly get soggier, but not actually like, you know? Does that make sense to everybody of why it's slower, not faster? Yeah, Porter.
I have two things.
Yeah.
One with pasta, is it like a kind of change of state because it's becoming softer or when you boil it?
It's more of a, I'd say it's more of like a chemical reaction with the noodle.
Okay, chemical reaction. And two, we wouldn't know if mac and cheese would really be made because we would die before that.
Yes. Cam and Easton have a smiley face though for sharing your thoughts. Okay, so now we're going to look at, so we looked at heating curves, which were about temperature. Now we're looking at phase diagrams, which bring them both into play. So this is known as a phase diagram, and you need to, they're all going to look similar, no matter what the substance is, but each substance has its own phase diagram. You need to understand what the different sections teach us, okay? So let's go ahead and label our phase diagram here. Okay, so first thing, the x-axis is temperature, so label that. X-axis shows us temperature. Y-axis is pressure, so let's compare pressure to temperature. This first section over here, this whole area represents the substance as a solid. So anywhere in that space, if you have like different colors, you could color in that whole area, that substance is a solid. Like, yes, like from this line up through that line.
Oh.
Does that make sense, Tony? Yeah, so that is all the solid. Blake, was that your question too?
Yeah.
Okay. This section up here, this skinny section, is the liquid portion of it. Which then means this whole bottom section would be as a gas.
What substance is this?
I think this particular one is, I think it's for nitrogen. I'm not positive off the top of my head, to be honest. But they all look similar. They all have like this weird Y-shaped thing going on. Sometimes the section might be bigger or smaller, but they'd all be similar. So. Oh, actually, I think, let me see, because I think we asked questions about it later.
Why are there arrows on the graph?
Okay, so that's the next thing I want you to draw. Okay, so draw two arrows right here. So anytime you go from this section over to this section, what's happening to it? How do you describe that process? Melting. Very good. Yeah. So anytime you cross from here to here, the substance is melting.
Or it's fusing.
And then going here to here, the substance is freezing. Yeah. So label melting freezing. Yeah, take.
What about 0 temperature and 0 pressure?
So here's the weird thing, right? So this is right now on, I think it's on like Kelvin is what temperature they're using. And absolute zero is the state at which a substance, and it's kind of a weird place that we don't know a whole lot about. Because at one point they thought it was impossible to reach it, but then they reached it and they went below it. And things got weird.
So it's not
Like-
absolute zero anymore?
Technically not because they went below it, but there wasn't supposed to be negative.
So what happened to it? Like, what did it do?
What
like-
happened? Like,
It's hard to explain because I don't even fully understand it. The article I read, so it happened actually, when did it happen? I guess it's been a bit, but it was the year, because I remember it happened the year I was student teaching, so like 10 years ago. And the article, it talked about that it like, if you know anything about space and antimatter or dark matter,
Oh, shoot.
it's kind of like what it started to do. Because it like did opposite of what. So yeah. So I don't know. There might be another state of matter besides solid, liquid, and gases, right? That we don't quite know how to explain.
Evil. Dark side.
Okay. Now, what's important to recognize, everybody, is that this entire line, okay, is the melting point and freezing point line. Because as we just saw, those points change as pressure changes, right? We say, oh, water freezes at 32 degrees. But that's not actually true because it depends on the pressure. It freezes at 32 degrees when you're at standard sea level. But if you're not at sea level, then it can freeze anywhere along that line. Or vice versa, or it can melt anywhere along that line, okay? All right, label over here, this next crossover. So anytime I cross from a liquid to a gas, I am, what's happening to the substance?
Evaporating.
Evaporating or boiling. Okay, so this one is the boiling line. And then opposite of boiling is condensing.
Condensation.
Yeah, like,
So, I feel like if this, like, there should be like solid, liquid, then gas, but then like solid and gas shouldn't be right next to each other. But it can only change states at the points that it's being stated at the blue and red line, at the blue and red arrows. It's the only place.
so it can change it, if I'm understanding what you're saying, so it can change anywhere along this line,
Yeah.
right? So if it's down here and it goes over here, it's boiling.
Yeah. But if it was like at 190, like 1 and 197.5, it can't change between a solid and a gas instantly.
It can. Yeah, I'm glad you asked that though.
Dang
So
it.
let's come down to this bottom section here. So you are able to change something straight from a solid
How is it even
into
possible?
a gas under the right conditions. I'll give you an example, or maybe I should bring some of this in too to see. You guys familiar with dry ice?
Yes.
So this is exactly what dry ice does. Dry ice is a solid, and if you just leave it sitting out,
It turns into
it just turns straight to a gas.
So
The process is called sublimation. So sublimation is going straight from a solid to a gas. So you are right, like it's unique. It doesn't happen for a lot of things under normal conditions. Obviously, if conditions are weird, it can happen, right? But with a lot of things, like with water, this V is much like lower down. There's a much smaller section, right, that it happens with. And then deep deposition is the reverse, taking something from a gas and turning it straight into a solid. So that's the opposite. So sublimation is going straight from a solid to a gas. Deposition is reverse.
what's a substance that has deposition that
So
is?
CO2 does the same. That's how they make dry ice. Is
Oh.
they just take the CO2 in the air and they pressurize it straight down.
Interesting. And then what is, so dry ice is literally just CO2.
Yep.
And then when it goes from solid to gas, the gas is just CO2.
Yep, still just CO2. Yeah, important to recognize here that everything we're talking about, it's not changing the substance, right? It's not a chemical reaction, it's just changing the phase. So, and keep in mind as we use the word normal, normal is referring to atmospheric pressure. So in Utah, we're not normal, we're not at atmospheric pressure, right? We're down at sea level for that. Okay, any questions so far before we keep looking at this graph some more? Okay, we're gonna label one more thing and then you'll flip your page over to fill in the blank. Okay? Put a little star or circle right at the point where they all meet. Okay? This right here is called the triple point.
What happens there?
The triple point is a very unique place where all three phases exist at once.
What is it? Whoa.
So you can have it.
Like a slushy.
So obviously it's not a point that would ever happen in like on Earth by itself. That pressure and temperature would have to be created in a lab setting. Like there's nowhere any substance is going to do all three. But if you could control it and controlling the pressure and the temperature to be it, you would see ice and water and gas all at once.
What is that even?
I don't.
Is there like a YouTube video on what that?
Oh look, there might be. I don't, cause my vacuum chamber I can't control the pressure. It's either nothing or everything.
It's all or nothing.
So I don't have like a thing that can control exactly what the pressure is. But I wonder if we can find a video on it. I'll look and see. Sam. Pretty much. It's pretty much like it would be boiling and then freezing and melting and boiling and
What?
freezing. All three exist at once. So. And then the second point I want you to label. Let's see if it shows it on here. Oh. So there's a triple point. So then also put a little dot at the end of this line. It's important to recognize that this line does not continue to infinity.
Interesting.
This is known as the critical point.
Right.
Okay, so this little dot at the end there is the critical point.
So what happens after that?
So the critical point is the point at which it doesn't matter how much pressure you have,
They will never go under.
it's going to be a gas. Like, there just gets to a point where it doesn't matter, and so it's just going to be, it's almost like it kind of goes slanted, but then you can almost imagine at that point, the line now just goes straight up. It's not like the line continues in its diagonal pattern past the critical point. But after that, it's just, once you get to this temperature, it doesn't matter, like it's just gonna be a gas.
If you have 304.26 Kelvin and you have like 18 billion pressure, it's still gonna be gas.
Yep. But you're better. I don't know if we can get to 18 billion pressure, so maybe that might break our graph. But you can assume, if you see here, like after that point, the line, you can kind of draw a dashed line, it just goes straight up after that. Questions on any points on our graph before we try some questions for systematics? Yeah.
So on the notes, it's like triple points, all blank phases coexist. What is that?
All three.
Okay.
Yep, so all three phases exist.
Well, isn't there more than 3 phases?
Yes. There's also plasma, but it's like
A
a
different.
different category.
Circle there.
Yeah, it's not like it's like. Okay, let's try some practice problems here with looking at the phase diagram. Okay? Alright, I'm gonna give you, I'll give you like 4 minutes. You can talk to your table buddy using the graph, see which of these you can answer on your own, but then we'll talk through them together. Okay? So skip down to the practice problems right there. Try 1, 2, 3, 4, and 5. And then we'll check them together, okay?
I said 75. It's somewhere between 50. As long as it's there, it's probably about right. We both reach 0.7 miles per hour.
I don't know exactly where that is.
Okay, let's walk through these. Obviously, I know I just wanted to see what you could figure out from graph reading without me, but let's make sure we understand it, as this is what you'll see on your homework, as well as like for the quiz this unit. Okay, so there's kind of like two different types of questions you can see with these. The first one is just what phase is it at under these conditions. So this is a match your X, match with your Y, see what section it lands in. So then it says, what phase is CO2 in at 200 Kelvin and 2 ATM? So you just come here, I know this is not the most accurate of graphs. You go to about 200, and then we're at...
Our graph is different.
Yours is different?
Yeah.
And our questions are different.
Well, that's annoying. What happened there?
Our questions as well.
We got them all right. Don't worry, don't worry.
Let me see if that graph shows up later.
Wait,
Okay,
do one
let's
more.
look at
Do
yours.
one more.
Wait,
It should, no, one more.
it doesn't go.
Oh.
No.
I don't know what happened. Okay, I'm going to go to mine though so you can see the idea of what you want to do, but we'll compare the answers for yours. Okay, so in this one, you're comparing just X, Y, line them up, see what section it lands in. So for mine, 2 and 200, so I would say in this case it's a gas. For your problem, it's 2 and 100 degrees, so you should have said solid. If you said solid, have a smiley face.
I think the measurement of 200 is a little wrong, but there is 197 on what's
Oh yeah, it's way down here. I think it still ends up being, oh actually it probably would be solid now too. Thank you, Lucan. That's why this scale's like way off because the numbers are weird. Okay, next one is similar. What is the phase of a substance at 0.75 and 100? So 0.75 and 100, I find that it's a liquid. Questions on that one? Have a smiley face if you got liquid. Okay, number 3, what is the phase of a substance at 1 atm, 1.5, and 800? So this one looks like, yep, it's a gas.
Oh, sorry.
So I have a smiley face for that. Now, the second type of question is the transition one. So that's what number 4 is. Where it's saying what phase change occurs when a substance at this, which was matching number 1, and then raising it to 500. So this is kind of where you find the first point, and then you move it in the direction that it says it's changing. So in this case, we're increasing the temperature, but maintaining the pressure. So to me, it looks like it changed to a liquid. So the phase change, though, would be melting. And then triple point
95 and 60.
is just find, yeah, it's kind of a little bit of estimate, right? 0.7 and 90 maybe?
It's 85.
It's 95. It's not 90.
Good. It's probably like 85.
No, I'm gonna
Sure.
I actually found a video
Of a triple point?
of water at triple point.
Oh, okay. On YouTube?
Yeah. It's just triple point of water UCSC physics. And then 114 is the timestamp.
Okay, any questions with graphs before we look at this little video? Okay, so your homework tonight is the one in your packet called phase changes, which has the first side practices with the heating curve, and then the back side is the phase diagram. So kind of practicing right there. It's like I think it's the 3rd page in here.
Yeah, and then go to 114.
Is this the beginning them like setting it up?
Yeah, so that's it slowly changing to it. And then 114 is when it actually changes.
What?
So what are they using to So it's like, it's, in a sense, it's like a vacuum chamber, but it's like a control.
It's getting
So you can like
close to it. This is it.
say
slowly
exactly
getting-
what pressure you want it to be.
So this is 4 times speed. You're now at.
So you can see, do you guys see the ice chunk in there?
What the heck?
So there's an ice chunk, there's water, but then there's also bubbles.
It's so cool.
And it's freezing at
Well, what the? What the?
I don't like
That is weird, huh?
It's so weird.
And does the air
That's not.
This is also at 4 times speed, but
Would you
I know.
eat it, or would you drink it, or would you breathe?
Look how, it's so weird how you can like, that's cool. Thanks, mine's not like.
of course.
Wait, yeah, what? If you went to like drink that, would you just like suck it in air?
Or would you eat, or would you
What?
eat solid?
Or would you be chopping on ice? Or suck it.
All of it at once?
Would it just be changing inside of like 40 years?